If you take a die, roll it 100 times, and count how many times each number gets rolled, you'll notice that every number between 1 and 6 gets rolled roughly the same number of times. No number is any more likely than any other number. But something bizarre happens if you roll 2 dice at once instead and add them together. The 2 dice can add up to anything between 2 and 12. However, their total will be 7 more often than any other number. Why on earth does this happen? This question is usually answered by looking at the 36 possible results you can get from rolling 2 dice. You start with a 1 and a 1, then a 1 and a 2, then a 1 and a 3, on and on until you get to a 1 and a 6. Then go through 2 and a 1, 2 and a 2, 2 and a 3, etc. Add the dice together as you go along, and keep a tally of how many times you see a particular sum. When you finish, sure enough, you'll get more tallies for 7 than anything else. But just going through all 36 possible outcomes and manually counting them is tedious. It becomes practically impossible, maybe even literally impossible for much larger sets of dice. Is there a better way to do this? As we try to answer this question, we will discover that even random events have subtle patterns. These patterns result from the central limit theorem, one of the most fundamental parts of probability and statistics. The central limit theorem is the pattern that makes 7 the most common roll of 2 dice. Casinos use the same pattern to guarantee that you lose. Factories use them to ensure that their machines produce high-quality products. And almost every scientific study ever uses the central limit theorem to come to conclusions. The source of this pattern is very far upstream, and it takes a while to hike into the mountains of math to discover where it comes from. But just like with any good hike, there are many breathtaking sights on the way up, each one more spectacular than the last. So I'll hope you join me on this journey to discover why the most common total of 2 dice is 7. To see this pattern, we need to notice that 7 isn't the only number becoming more likely. Let's take the tallies we made and put them into a graph of the probabilities of rolling each number between 2 and 12 with 2 dice. The graph we get forms a pyramid with the highest odds concentrated in the middle. 7 is in the middle of the pyramid, so it's the most likely outcome. By the way, we'll see many probability graphs in this video. It's important to note that mathematicians like to call them distributions, since the graph is telling you about how the probability is distributed across all the different possible totals of the dice. While we're talking about terminology, it's common to call random number generators like dice and parts of video games random variables. This is because things that are unknown or change are called variables, and numbers generated randomly are, well, random. Each random variable has a unique distribution of its outcomes. In the case that we've been looking up, the dice sums are the random variable, and the graphs we've seen are their associated distributions. If we look at the distribution of one die, it's not a pyramid, but a flat line. When we add in the second die, the probability moves from the graph's edges into the middle, and it creates the pyramid that we saw before. But what's even more interesting is what happens when we throw in a third die. The same thing happens. The probability gets moved from the edge of the graph and dumped in the center again. And it happens again if we add in a fourth die, and again if we add in a fifth die and a sixth. In fact, we can keep adding dice up to infinity and the same thing keeps happening. Also, notice that as we add more and more dice, the shape of the distribution changes less and less. The first two distributions shift a lot, but once we've added several dice, the form of the distribution changes less and less. Now, there's a bit of a caveat to these distributions I've been showing you. I'm not actually plotting the probability of getting each outcome on the y-axis, but I am plotting something analogous to the probability. If I were to just plot the probability, then this is what it looks like if I compare the distribution of 1 die to 2 dice. In this comparison, it seems like the bars of the graph of 2 dice are generally shorter than the graph of 1 die. Hence, it looks like the total probability of 2 dice is less than the total for 1. This obviously can't happen because the total probabilities must add up to 100%. The probabilities for 2 dice do add up to 100%, and we can see this if we pile the bars on top of each other. We can see that the total height of 1 die and 2 dice add up to the same amount. Still, we can see why the bars looked shorter. The bars we stacked for 2 dice are thinner than the ones we stacked for 1 die, so each bar takes up less physical space. There are more bars for 2 dice than for 1 die, so the bars need to be thinner to be plotted on the same interval. To compensate for this thinning, I'm stretching out the height of the bars for 2 dice so that the total area of all the bars is the same. Doing this makes the pattern that emerges much easier to see, and also turns out to be helpful for thinking about probability distributions with continuous curves rather than discrete outcomes. This value is known as the probability density because it tells you how much probability there is per unit length of the x-axis. Anyway, back to the graphs we saw. Clearly, there's some sort of pattern going on here. But before we can learn about this pattern, we must first answer an important question. Why should we care? We can see this pattern emerging, but why is it so important? Well, randomness is, by definition, the absence of any patterns. No strategy exists that will ever tell you whether a coin will come up heads or tails because it's random. But here, as we add more and more dice rolls together, we definitely see a pattern emerge. Even though there are no patterns in the dice individually, a pattern emerges when we add them together. Imagine if, when you flipped a coin, there was a pattern in which side came up. Maybe the coin always shows the opposite face that it landed on the last time you flipped it. In that case, you would know with certainty which side the coin would end up on, and you could predict the outcomes of the coin. The central limit theorem states that 3 patterns can be found in any random event with enough repetition. These patterns aren't as simple as those I just mentioned for flipping a coin. However, unlike the coin flipping example, which is made up nonsense, the central limit theorem is real. In this video, we'll discover these patterns by seeing them in dice and trying to find out what it is about adding dice together that causes them to emerge. Doing this takes meaningful time and some wonderful and unexpected connections between our dies and sinusoidal functions. We'll start out by simulating dice rolls and trying to spot some patterns in what we get. We'll then find a way to formalize what we mean by the sum of any number of dice and discover a trick that will make it much easier to calculate. And we'll end by seeing how the patterns we've found by simulating dice are all natural consequences of our equation for the sum of n dice. We'll then use what we discover to explain why the most common total of 2 dice must equal 7. Let's begin our search for patterns. We've already seen that as we added more dice, the shape of the distribution changed less and less until it had taken on a particular form. This looks like it could be a pattern. Hence, a natural question we might have is whether this is a special case, or have we struck some pattern that applies to all random variables? Remember, random variable is just fancy talk for random number generator. To see if this is a pattern, let's try a random variable with a different distribution and add it up in the same way that we added up the dice and see what happens. One way we could do this is by weighing specific outcomes of the dice, so that certain numbers are more common than others. Weighing, by the way, means using some sort of carefully designed die that lands on certain numbers more often than normal. This is usually done by putting some sort of heavy weight into the opposite side of the die so that it lands face down, which is why it's called weighing a die. This would change the distribution of the die, so it might also end up changing the distribution of its sums. There are infinitely many ways that we could weigh a die. which one should we choose? Well, remember, our goal is to find out if the pattern we saw with a fair die generalizes to other kinds of dice. So let's try and choose some weight that we think might break the pattern we see. If we're seeing a special case for a fair die, the pattern will hopefully disappear. Here's a weight distribution I came up with that's decently asymmetrical. A 50% chance of rolling a 5, a 25% chance of rolling a 6, a 10% chance of getting a 3, and a 5% chance of getting anything else. Now, in a second, I'm going to graph the odds of getting different totals as we add more dice. But first, I want you to pause for a second and make a prediction about what you think will happen before I show you. Will the things we've done to the distribution break the pattern, or will the pattern continue? Pause and make your guess. Let's stop and compare the fair dice to the weighted ones. Oddly enough, even though a single weighted die has an asymmetric graph of probabilities, what we've ended up with is symmetrical. But even more interestingly, look at the shape of the two distributions. They look somewhat similar to each other, wouldn't you say? Furthermore, the shape that both graphs converge to is not the original shape they had. The fair die started out as a flat line, and the weighted die started out as a weird asymmetrical mess. But they both turned into this bell shape. In fact, no matter what sort of wonky distribution you give the dice, the sums of those dice will always be some sort of variation of this curve. Now, as I add more and more dice to this simulation, the amount of work the computer has to do grows exponentially. Each new die creates 6 times as many outcomes as we had before. But imagine if we could come up with some sort of closed-form equation for this curve we just discovered. We could approximate the probabilities using that equation instead of doing the thousands of iterations that I'm doing now. So let's see if we can come up with a closed-form equation for the curve we see. There's a bunch of properties that this curve has that give us hints about what that equation could be. If you want a challenge, try pausing the video and see if you can come up with a few of them on your own. One of the first things we notice is that this function has strictly positive values, because we're graphing the probability density, which must be a positive real number. However, this also means that whatever function we come up with must also generate positive real numbers. The edges of this graph also look pretty similar to an exponential function. Exponential functions also just so happen to produce strictly positive numbers for real inputs. So a good first guess might be that the equation for this graph contains some sort of exponential function. If we're looking at an exponential function, something we could try doing to gain more insight is to take the natural logarithm of all the points. Suppose the equation looks like e raised to the something. In that case, taking the natural logarithm will undo that step. We'll be left with whatever function was passed into the exponential at the end. So let's apply a natural logarithm and see what happens. The graph is almost a perfect parabola. You also might have guessed that this would happen because the curve that we're trying to model has a single global maximum. Either way, we can be reasonably confident after seeing this that the generic equation we're looking for is some sort of exponential function applied to a parabola. All parabolas have a generic formula with 3 coefficients. By modifying these coefficients, you can move the curve all over the place. Here is one generic formula for a parabola, called a parabola's vertex form. This vertex form helps us visualize how we can move a parabola around. If we change A, it scales the graph horizontally. If we change B, it shifts the graph horizontally. And if we change c, it shifts the graph vertically. We can also look at how these coefficients change the parabola after we pass them through the exponential function. If we change a, it stretches the graph horizontally. If we change b, it shifts the graph horizontally. And if we change c, it stretches the graph vertically. Remember how the graphs of the weighted and unweighted dice look the same, only shifted and pulled? Wouldn't you say that it makes sense that the underlying difference between the weighted and unweighted die is that the coefficients of their parabolas are different? As we play around with the graph, there are a few cases where our graph represents a physically impossible probability distribution. For example, if a is positive, our graph explodes to infinity. It can't represent a probability distribution, so we have to assume that a is negative to give us a nice confined graph. Another problem is that, as we said earlier, the total area under the graph must equal 1. This is because the area under the graph corresponds to probability. As we will see much later, it's very important that all the probabilities add up to 100%. If we stretch our graph vertically, it will also increase the total area under the curve, so we aren't free to set c to whatever we want here. We need c to equal whatever it needs to be for the total area under this parabola to equal 1. Similarly, if we stretch the graph horizontally, it will also change the area under the curve. But we can compensate for this horizontal stretching by squishing the graph vertically so that the total probability remains 1. This will mean that our c parameter will turn out to be some sort of function of the a parameter. Now, I'll skip over the details of how you make sure that the parameter c follows all those rules, but later on I'll have an animation that shows some of the steps of finding the area under that curve. The answer is that c equals the natural logarithm of 1 over the square root of pi times a. Yuck. We can now do some properties of exponents and find that we can pull out the natural logarithm in front of our equation. This equation is still pretty gross, but there's one more modification that's usually made to it. Instead of coefficients a and b, statisticians like to use these two parameters called mu and sigma. For our purposes, mu is just equal to b, and a equals 2 times sigma squared. The equation we get when we substitute mu and sigma for a and b is one of the most important equations in all of statistics. The equation for Gaussian distribution. Gaussian distributions are so common in probability and statistics that they're also called normal distributions because it's incredibly normal for them to appear. The first pattern that the central limit theorem predicts is that no matter what the underlying distribution of the dice is, the distribution that emerges will approach a Gaussian distribution. The central limit theorem is why the Gaussian distribution is so typical. But where does it come from? How does this curve have anything to do with adding dice together? To answer these questions, let's formalize the idea of adding 2 dice together. Let's say I want to know the odds that 2 dice add up to 9. Is there a way that we could calculate the probability of a 9 without looking at every possible way that the dice could land? One way that we could do this is to only calculate the probabilities of outcomes where the dice do add to 9. We can take all the probabilities of getting a 9 and add them all together to get the total probability of getting a 9. This way, we can skip the work of going through the remaining outcomes. To do this, we need to be able to list every possible sum that adds up to 9. Luckily, there's a trick to doing this. Let's call the numbers that we roll on the 2 dice s and t. Saying that the dice add up to 9 is equivalent to saying that s plus t equals 9. We can solve this equation for s and get that s must equal 9 minus t. To get the probability of rolling a 9, we go through every possible value that t can take. For each t, we multiply the chances of the first die getting a value of t by the chances of the second die getting a value of 9 minus t. When we add them all together, we have a closed-form equation for the probability of rolling a 9. Now notice that there's nothing special about the value 9 here. This argument works for any number, so we can replace our 9 with an x. Also, since I'm using p of x inside of this sum, I'm going to rename p of x on the outside to p2 of x, just to make it clear that we're talking about two different functions. An important point to note here is that we're calculating the odds of rolling a t and an x minus t by multiplying their probabilities. This is the most common way that people compute the chances of two things happening simultaneously. Still, importantly, it's not necessarily true. An excellent example is whether or not it snows in two nearby cities, each of which has a 1% chance of snow. If you multiply the 1% odds of both cities, you might conclude that the odds of snowing in both places is 0.01%, or 1 in 10,000. But if it's snowing in one of the two, it's probably also snowing in the other one, since the towns are close. So multiplying the odds together gives you the wrong answer. Because this equation for rolling a 9 multiplies the probabilities, it implicitly assumes that the odds of the dice are independent. All of the constructs that we build on top of this equation to see why the Gaussian curve emerges will only hold true if this assumption is accurate. So this equation we've come up with is a way to turn the distribution of individual dice into the distribution of their sum. But to some of you, this summation might look familiar because it turns out to be an operation that appears in a bunch of pieces of math. This operation has a particular name, the convolution operation. Convolution is an operation that takes in two functions and sort of merges them together into a single function. In our case, the convolution operation takes in the distributions of the dice and gives us the distribution of their sum. Convolution is usually denoted by putting a star between the two convoluted functions, which is a terrible notation because it looks like you're multiplying the two functions. Convolutions appear in many different fields, including signal processing, machine learning, and, as we've just seen, probability and statistics. Usually, convolution is defined with an integral instead of a sum, using continuous functions rather than discrete ones. Still, the general form of the equations is the same. Convolution gives us a really nice and simple way to formalize the sum of two random variables. For any two random variables, the distribution of the sum of those random variables equals the convolution of their distributions. Convolutions have a deep and beautiful connection to something entirely unrelated to probability and statistics: sinusoidal functions like sine and cosine. Now, just the fact that there's a connection between rolling dice and wavy functions is not apparent at the outset. Usually when we see sinusoids, we're dealing with rotation or waves. But when you apply this convolution thing to two sinusoidal functions, something interesting happens. Let's look at a cosine curve. If we take a single oscillation of this wave, we can see that the total area above y equals 0 is precisely equal to the area beneath y equals 0. So the total of the two regions equals 0. The entire cosine of x graph consists of an infinite number of these cycles. So the integral of the whole graph equals 0. This property makes it so that there's an easy trick to calculate the convolution of two sinusoidal functions. I'll take the convolution of two cosine waves with frequencies omega 1 and omega 2. I can do this by plugging the two functions into the integral that we saw a second ago. Under the integral, we now have the product of two cosine curves to which we will apply one of the seemingly endless trig identities. In particular, I will use this one for cosine of A times cosine of B equaling the sum of these two cosines divided by 2, and remove the common factor t from the omegas in both cosines. Now, here's where the fact that the integral of a sinusoid equals 0 comes into play. In most cases, these two integrals will equal 0 because both of them are integrals of cosines. However, there's a special case where the integral does not equal 0. Suppose omega 1 and omega 2 are equal. Then the quantity omega 1 minus omega 2 that t is multiplied in the first integral equals 0. That means that now the cosine isn't a function of t. It's just a constant cosine of omega 1x, which is non-zero. The other integral is unchanged, but the result is that the convolution of the cosines is non-zero. Now, it turns out that this factor of a half is actually incorrect, so I'm just going to get rid of it, but I won't go into the details of why. A challenge for you in the comments: explain where the factor of a half comes from. A hint: there's another case where the integral does not equal 0. See if you can find it. So long as they have different frequencies, the convolution of any two sinusoidal functions will always be 0. Furthermore, it's elementary to prove that if the two functions have the same frequency, then their convolution will be a sinusoid that has the same frequency, an amplitude equal to the product of the amplitudes of the sinusoids, and a phase equal to the sum of the phases of the sinusoids. This result has the sweet smell of complex numbers about it. So taking the convolution of two sinusoids is easy. It's either 0 or another sinusoid with these simple formulas for its new amplitude and phase. This is nice if we happen to be working with sinusoids, but most functions in the real world, including the distributions of the totals of dice that we care about, are not sinusoidal. So we can't use this result for them. Or can we? One of the most important pieces of math ever discovered is that any function you can take an integral of can be broken apart into an infinite set of sinusoids. This includes our function for the distribution of our dice. We can do this trick with any probability distribution, even the messy distribution from our weighted die. Instead of going through this messy convolution sum thing, we can split our function into a bunch of these sinusoids and apply the convolution to the sinusoids. All the sinusoids with different frequencies will combine to 0, and all the sinusoids with the same frequency would multiply as I described earlier. We could then add those sinusoids back together and get the convolution of our two functions. Taking a function and breaking it down into a sum of sinusoids is called taking a Fourier transform. As I mentioned before, Fourier transforms are one of the most crucial pieces of math ever discovered. But the best description I've ever heard of just how broadly applicable Fourier transforms are came from my favorite professor in college. He liked to describe Fourier transforms as mathematical snake oil. Snake oil was a fake remedy that shady salespeople in the Old West used to proclaim would cure any ailment. Have a backache? Rub some snake oil on it. Having a hard time falling asleep? Drink a little bit of snake oil. Unsure what the distribution of the sum of n dice is? Just rub some of this mathematical snake oil on it, and it suddenly becomes infinitely simpler. The range of problems that Fourier's ideas are helpful for is just as broad as the kinds of ailments that snake oil was supposed to cure. And it makes all those problems just as much easier as a snake oil salesperson would lead you to believe. The Fourier transform is a bit like a mathematical machine. You put some sort of generic function into the machine, and it finds all the sinusoids that will add together to create that function. It will then give you a different function that lets you look up what those sinusoids are by their frequency. We write the process of putting a function through the Fourier transform machine by putting our function inside of curly brackets and putting an f in front of them. We read this as the Fourier transform of f of x. It's also convention to call the function the Fourier transform gives us back f hat of omega. So this equality would read the Fourier transform of f of x equals f hat of omega. Also, note that the new function takes in frequency as its input, which I'm denoting with an omega. If you were to evaluate f hat at a value of 1 Hertz or 2 pi radians, it would give you back the magnitude and phase of the sinusoid it came up with that has a frequency of 1 Hertz. The Fourier transform packages the amplitude and phase of the sinusoid as a single complex number, which is really convenient for us. We just saw that the convolution of two sinusoids causes their amplitudes and phases to combine in a way that looks like complex multiplication. Let's formalize the sinusoid trick we were just talking about. If we have two functions, f and g, that we want to find the convolution of, we first find their Fourier transforms, then multiply them together. We then undo the Fourier transform and get the convolution of the two functions back out. This result is so ubiquitous in fields that use convolutions that it's literally called the convolution theorem. If we add n dice together, we know that the distribution of the sum of those dice will be the distribution of a single die convoluted with itself n times. But now, let's take the Fourier transform of all those convolutions. F of x convoluted with itself n times turns into f hat multiplied by itself n times. In other words, the Fourier transform of the sum of n dice is equal to the Fourier transform of one die raised to the power n. That totally blew my mind when I saw it. Now that we have a precise way to express the sum of n dice, let's see if we can explain why the earlier patterns emerge. And this is where the experiment we did earlier is beneficial, because we know what pattern we should expect to see. We know that the sum of n dice was approaching this Gaussian curve. If that's true, we should expect that the Fourier transform of the sum of n dice is the same as the Fourier transform of a Gaussian distribution. In particular, this should be true in the limit as n goes to infinity. Once again, our experimenting comes in handy. We know the generic formula for a Gaussian distribution, so we can just take that equation and send it through the Fourier transform machine right now. And we'll get back the exact equation for the Fourier transform of the Gaussian distribution. I know that I've probably lost a lot of you by sneaking calculus into this video already, so I'm not going to explain how we use the Fourier transform machine. But if you are interested, I'm going to animate the calculus autopilot for finding the Fourier transform of the Gaussian. Feel free to skip ahead if you don't know calculus or aren't interested. So the Fourier transform gave us another exponential function. It still looks disgusting, but let's proceed. Our objective is to show that the Fourier transform of a Gaussian distribution equals the Fourier transform of our dice raised to the power n, as n goes to infinity. Now, it's not obvious that the two sides will be equal, but there is one thing they have in common. They both use exponents in some way. On the left, this Fourier transform is raised to the power n, and on the right, we have an exponential function. We could quickly eliminate these exponents by taking the natural logarithm of both sides of the equation. But this presents us with a new problem. On the left, the quantity that we're taking the limit of now has a factor of n out front. As n goes to infinity, the left side will explode off to infinity. This implies that the two sides of the equation are not equal, which is true. The two sides of this equation are not equal in general. So, all the work we've done was for nothing? Well, no. What we have is not identical, but it's very close to equality. We can make a few subtle changes to this equation that will turn it into one. We'll get to what those changes are in a minute, but let's just pretend that the left-hand side isn't going to infinity, and we'll try and draw some connections between the right and left. One thing that really sticks out is that the Gaussian distribution has turned into a polynomial. It's trivial to show that two polynomials are equal to each other. All you need to do is show that all the coefficients of the polynomials are equal. The problem is that, once again, that's nice if you happen to have two polynomials, but most functions in the real world, including the natural logarithm thing we have on the left, are not polynomials. So we can't compare their coefficients. Or can we? Another of the most critical pieces of math ever discovered is that any differentiable function can be broken down into an infinite polynomial called the function's Maclaurin series. Once again, we can do this with the thing we're working on. So our Fourier transform is equal to the sum of a whole bunch of powers of omega multiplied by a whole bunch of constants. For the moment, we don't really care what these coefficients are, and we'll see soon that it doesn't really matter what they are. It just matters that they exist. We can also think of the Gaussian distribution as an infinite polynomial. We just say that the coefficients of the higher order terms are all equal to 0. So if we can show that the coefficients approach the coefficients of a Gaussian distribution, it would prove that the sum of n dice approaches a Gaussian distribution. We know that the sum of n dice will be this polynomial multiplied by n. So we can get the power series for n dice by distributing that factor of n to all the coefficients for a single die. This factor of n is causing the whole thing to explode to infinity. I think it's time we'd fix that problem. To understand what's going wrong, we must remember that I lied to you a bit to make the graphs at the start of the video. I was squishing the x-axis of the graph so I could put them on top of each other. Here's what it looks like if I don't squish the graphs. As you can see, the graph just explodes off to infinity. No wonder the Fourier transform was exploding off to infinity. We weren't squishing it back into place. It takes a lot of work to find the Fourier transform. Just ask the people who sat through the process of finding the Fourier transform of the Gaussian distribution. Reusing the sinusoids that our Fourier transform found would be much more efficient. So if we could squish the graph by a factor of k, what effect does that have on the sinusoids that make it up? Well, let's take a look, shall we? It's pretty clear that all that's changing is that the sinusoid's frequency is scaled by whatever factor I squish the graph. The amplitude and phase we associated initially with one frequency are now associated with a new frequency. And that new frequency is equal to the old frequency multiplied by the scaling factor. So let's say I wanted to find the magnitude and phase of a new frequency using the old Fourier transform. All I would need to do is divide the frequency by whatever factor I scaled the graph and look up what that frequency is in the old Fourier transform. For my next magic trick, let's return to the power series we were looking at. We said that scaling down our distribution would have the effect of evaluating our original Fourier transform at omega divided by n. So let's replace all the omegas in our series expansion with omega divided by n. Now check this out. As n goes to infinity, each term with an n in its denominator goes to 0. So almost all of the infinite terms of the polynomial go to 0. Squishing the distribution back into place causes this natural logarithm thing to approach a polynomial as n goes to infinity. And we've already seen that the Gaussian distribution turned into a polynomial. However, this still isn't equality. Notice that the Maclaurin expansion doesn't have an omega squared term. If the two sides of this equation are equivalent, it would mean that the parameter sigma for our Gaussian distribution is always 0, which it obviously isn't. So, is there some way we can stop this second term from going to 0, but still get rid of all the other terms? And there is. We can divide our distribution by any factor we want, not just n. So if we wanted to, we could divide our distribution by the square root of n instead of n. This causes the polynomial we get to be of order 2, while still killing all the other terms. So all that's left for us to prove is that the coefficients of our Maclaurin series equal the coefficients of the Gaussian distribution. Let's imagine that we evaluate our polynomial at omega equals 0. In that case, all of the omegas in our series expansion evaluate to 0. And on the right, the only thing we're left with is kappa 0. Therefore, the coefficient kappa 0 will just equal whatever our natural logarithm evaluates to when we plug in omega equals 0. But this immediately gives us a problem. So far, we haven't evaluated the Fourier transform at any particular value. Our expectation from our experiments is that we should get the same results regardless of the distribution. But if we evaluate the Fourier transform at a particular value, that generality would be lost. But luckily for us, we aren't just evaluating the Fourier transform of a generic function. We're taking the Fourier transform of a probability distribution. And any probability distribution will always evaluate to the same thing at omega equals 0. To understand why this is, we must first understand what it even means to evaluate the Fourier transform at 0 frequency. Let's look at a cosine wave and put in that it has a frequency of 0. No matter what x is, we will always evaluate the cosine at a value of 0, which just turns it into a constant 1. Multiplying the whole thing by an amplitude just gives us a constant which our remaining sinusoids are added to. Now, let's imagine that we were to take the integral of our probability density function and calculate that integral by calculating the integral of all the sinusoids that our function has been split up into. Earlier, we saw that the integral of any sinusoid from minus infinity to infinity always equals 0. So the integral of almost all sinusoids is 0. But there's one exception, the constant term. The integral of the constant term is the only part of the entire integral that doesn't equal 0. Therefore, the integral of all the sinusoids must just equal whatever the constant term is. So evaluating the Fourier transform at omega equals 0 equals the integral from minus infinity to infinity of our function. But here's the thing. The integral of any probability density function equals the total probability of all possible outcomes. And the total probability of all possible outcomes is always 1. No matter what kind of wonky distribution come up with, its probabilities must add up to 1 for it to represent probability. And because the probabilities must add up to 1, the Fourier transform will also evaluate to 1 every time. We can now take the natural logarithm of it, and we get that our limit will always equal 0 for omega equals 0. So kappa 0 always equals 0. We can now plug kappa 0 into our Maclaurin series and simplify. Simplifying also conveniently gets rid of this annoying factor of n that was technically causing our sum to explode to infinity. Now, there's still this annoying factor of square root of n that's causing this thing to explode to infinity, and I'm going to ignore it because this video is already way too long. Essentially, it boils down to assuming that kappa 1 equals 0, but I'll leave it as is because there's still some magic I want to show you about kappa 1. The coefficients of the second equation can be whatever we want them to be. We can just choose mu and sigma such that this equality holds if we wish to. All they do is shift around where the Gaussian distribution is, so we'll always be able to find some Gaussian distribution such that this equality holds. This also proves why different distributions will converge to different values of mu and sigma. The coefficients of the power series of different functions will be different, so their values of mu and sigma are also going to be different. It would be nice to know how to calculate mu and sigma so that we can choose which particular Gaussian distribution we should use to approximate random variables with. We can do this by finding the values of the coefficients kappa 1 and kappa 2. We'll use the Maclaurin series to find kappa 1 and kappa 2. This is done by taking the derivative of our natural logarithm thing and evaluating it at omega equals 0. We can then use our trick to evaluate the Fourier transform at omega equals 0, and then we can take the second derivative and do the trick again. That's all we need because all the other coefficients will eventually go to 0. This is great, but how do you take the derivative of a Fourier transform? The answer is that you essentially take the derivative of each component sinusoid on its own and then add them back together. So let's look at a single sinusoid on its own. A times cosine of omega x plus phi. The most important thing about taking the derivative of a Fourier transform is that the input of the Fourier transform is the frequency of the sinusoid, not the point that we evaluate the sinusoid at. So when we take the derivative of our sinusoid, we take it with respect to omega and not x, like you usually do in calculus. So we get the derivative by applying the chain rule, and we get minus a times sine of omega x plus phi. Taking the derivative has the annoying effect of changing our cosine function into a sine, which is slightly inconsistent. Ideally, we'd like to have only one kind of sinusoid in both the normal function and its derivative. Now, this whole time, I've been acting like the Fourier transform generates cosine waves, but it actually doesn't. Instead, the Fourier transform generates complex exponential sinusoids, stuff like a times e to the minus I omega x plus phi. And if we take the derivative of one of these functions using the same process, we get the original sinusoid multiplied by minus I times x. The fact that we've changed from cosine to sine is encapsulated in the factor of minus I that we get out front. Here's the crucial insight. Let's add all of the complex exponentials back together and restore the original function. Each one of these complex exponentials is multiplied by a common factor of minus ix. So we can pull that common factor out from all the sinusoids, and we're left with just the sinusoids from our original function before taking the derivative. but when we add them back together, we get our original function. So the derivative of the Fourier transform just corresponds to multiplying our original function by minus ix. So let's say that we wanted to evaluate the derivative of our Fourier transform at omega equals 0. We can use our last trick to evaluate it at omega equals 0 by just taking the integral of the original function. Therefore, the derivative of the Fourier transform evaluated at omega equals 0 just equals the integral of the initial function times minus ix. Isn't that neat? And we can do this a second time to evaluate the second derivative by just multiplying by minus ix a second time. Now, let's find the first two derivatives of the natural logarithm of the Fourier transform and evaluate them at omega equals 0. We can use the chain rule for the first derivative, and we get 1 over p hat of omega multiplied by the derivative of p hat of omega, which we can just write as a fraction. We then need to take the derivative again to get the second derivative, which we can just do using the quotient rule. Let's now take the equations for the derivatives and use them to find kappa 1 and kappa 2. The Maclaurin series tells us that we need to divide each kth derivative by k factorial. And so that just means dividing the first term by 1, which doesn't change anything, and dividing the second derivative by 2. We now need to evaluate all the different p hats and p hat derivatives at omega equals 0. We've already seen that p hat itself, evaluated at 0, just equals 1, so we can replace all of them with 1s. We're left with a lot of divided by 1s, which we can simplify very nicely. We can now use our trick that we discovered to evaluate the Fourier transform's derivatives. We take the integral of minus ix times p of x to get the first derivative. We can pull out a common factor of I, and we're just left with the integral of x times p of x. Now, most of you who have taken a probability class at this point are probably having light bulbs turn on in your head. But to be as transparent as possible, let's modify these equations a little bit. Let's return to the discrete case and look at equations as sums instead of integrals. Do you see it yet? Here's one hint. Think of the probability here as the weight that you're giving to a particular value of x. In that case, what this equation is doing is calculating the weighted sum of x. In other words, this is calculating the average that x takes, more particularly the mean. So this integral is really just the mean of x. But wait, there's more. You see, the standard letter used to denote the mean of a probability distribution just so happens to be the Greek letter mu. Oh, what a coincidence! It just so happens that there's a parameter from our Gaussian distribution that's also called mu. And wouldn't you know, it looks like it's multiplied by a minus I in the first term of the equality. Well, wouldn't you look at our equation for kappa 1? It also happens to be multiplied by a constant factor of minus I. Let's go further. Sigma also just so happens to be the Greek letter that is associated with another famous quantity from statistics, the standard deviation. How much do you want to bet that when we evaluate the second derivative, we're going to get the equation for the standard deviation squared? If we look at the equation for standard deviation, we can see that it actually already contains a square root in it. So squaring sigma just has the effect of getting rid of this square root. In fact, it's actually common in statistics to use the square of the standard deviation for calculations, and this is a prime example of why. The square of the standard deviation shows up a whole lot more in probability equations than the standard deviation itself. Because the standard deviation square is used so much, it has its own name. It's called the variance. Back to our math. We also want to switch from the discrete case to the continuous case, which just means using an integral instead of a sum. And from here I'm just going to switch to Algebra Autopilot. So now let's compare this equation to the kappa 2 that we got from the quotient rule. Wow, that's pretty spot on, isn't it? Sure, they differ by a factor of -1/2, but if you look at the equation for the Gaussian distribution, you can literally see that it is sigma squared multiplied by, you guessed it, a factor of -1/2. So the coefficients of the power series are just the mean and variance of the distribution multiplied by some constants. Now, remember how we showed that if we added n dice together, each coefficient of the power series would be multiplied by a factor of n. Since these coefficients include the mean and variance, it logically follows that when you add n dice together, their mean and variance will also be multiplied by n. So the mean and variance of the sum of n dice will always equal n times the mean and variance of a single die. To summarize, we've just shown that the distribution of the sum of n dice will approach a Gaussian distribution, and that the mean and variance of the sum of n dice will always be n times the mean and variance of a single die. We can therefore approximate the sum of n random variables as a Gaussian distribution with mu equals n times the mean and sigma squared equals n times the variance. What I just described is the central limit theorem as you would see it in a class on probability and statistics. And we can now finally use the central limit theorem to answer the original question. Why is the most common total of 2 dice 7? We can approximate the sum of 2 dice as a Gaussian distribution since it is the sum of some number of dice. The most likely outcome of a Gaussian distribution occurs at the parameter mu. We can quickly calculate the mean of a single die by multiplying all of the outcomes by their probability of happening and then adding them all together. So the mean of 2 dice is 3.5 times 2, which equals 7. Therefore, 7 is the most likely total of 2 dice. Now, that argument is a bit shaky, but it's mostly okay, and I think we've all had enough formal mathematics for one day. I hope you enjoyed this journey to discover where the central limit theorem comes from, and I hope you learned something new. Thank you to Grant of 3 Boo 1 Brown for inspiring us to make this video and holding the SoMe 2 event. The two of us met through the SoMe 2 GitHub, and we would have never met each other otherwise. If you like the video, you'll probably like some of the other SoMe 2 submissions, so check the playlist on screen now or in the description.